Now I will move to chapter 7, and with chapter 7 we are going to start including more types of energy, like gravitational potential energy and elastic potential energy. Then today we are going to learn how to use gravitational potential energy in problems that involve any vertical motion, because gravitational potential energy has to do with the vertical motion. Also, we are going to learn how to use elastic potential energy, and that is when we have a spring that is stretched or compressed in the problem. We will distinguish or differentiate between two categories of forces: conservative forces and non-conservative forces, and we're gonna learn how to include all of them in the conservation of energy. We're going to understand also how to use energy diagrams to understand how an object moves under the influence of a conservative force. And we are going to start now, and maybe this is one of the introductions, related to maybe any, it doesn't need to be a sandhill crane, or like it can be anything that is changing its vertical position, how really this is going to be reflect on its energy, and how it's going to reflect on transforming of the energy from one form to another. Now, gravitational potential energy, it is just because the Earth has its gravitational field around it, then we are going to have that gravitational potential energy related to the object that is in that field. Now, the gravitational potential energy, I will call it UG, equals m times g times y. Remember, gravitational potential energy, it is a scalar. No signs here, they're gonna be, unless we are going to use our reference for the gravitational potential energy below the zero. Now, we need always a reference to measure y from. Okay, sometimes it might be the ground. Sometimes I might use the table if I'm doing my work on the table. M, it's the mass, and it should be in kilogram. G is gonna be the acceleration due gravity, and just remember here it's the magnitude of it, 9.8. Yeah, of course it depends on my significant figures, 9.8 or 9.80, and y is the vertical distance, and that vertical distance, it is measured from a reference. As this basketball is descending or moving downward, the gravitational potential energy is decreasing because I have y is decreasing, and of course we will not say it will be lost, it is converted into kinetic energy, and this is going to reflect on the basketball as its speed is going to increase. Okay, the change in gravitational potential energy, it is related to the work done by gravity, and actually we are going to also find, I will say, like an expression that is relating the force with the change in the gravitational, in the potential energy. We will talk about it later, but here we have in that object is moving downward, and then I will say y decreases, then y1 is greater than y2, and w, okay, the work, the weight is doing positive work. Okay, why it is doing positive work? Because the weight is downward and s is downward, and but delta u is going to be less than 0. Okay, and this is really how they are really related. Now, when the object is moving upward, y increases, and then the work done by the gravitational force is negative because the weight is downward and the displacement is upward, and the gravitational potential energy increases. And then always they're going to have opposite signs. Okay, let's work on this problem here. I have a 90 kilogram mail bag hangs by a vertical rope that is 3.5 meters long. A postal worker then displaces the bag to a position 2 meters sideways from its original position, always keeping the rope taut, which means like the length is not going to change. What horizontal force is necessary to hold the bag in the new position? As the bag is moved to this position, how much work is done by the rope and by the worker? Now, this is the situation. This is the, the postal, the mail bag. It is here attached to the string, and that length, it is 3.5. It was moved a horizontal distance that is 2. Here is the diagram that is going to show us what really the relation between the distances. That whole thing is 3.5, and it was moved that 2 meters here. I need to find that h here, and I will say we can calculate theta as sine inverse of 2 meters divided by 3.5, because this is going to be 2 meters, and then okay, this is the theta, then this is the opposite to theta, and this is the hypotenuse. Then I will be able to calculate the theta as 34.8, and then I can say cosine theta, which is cosine 34.8 equals y prime divided by 3.5, and my y prime is going to be 2.87 meters. When I say y prime, I am looking at that here distance. This is the one. So that I will be able to calculate that h as 3.5 minus 2.87 meters, which is going to be 0.626 meters. Then this is like I did all this here just to find how much it was elevated. Now the forces on that postal thing, it is the force that the worker applied to the rate, the tension from the rope, and its weight. And we know that this angle here, it is 34.8. Now, the first question is asking about what horizontal force is necessary to hold the bag in the new position. Then I need to do kind of Newton's first law. Here I can say T cosine 34.8 should balance mg. This is sigma Fy equals 0. And horizontally, the magnitude of the force should equal T sine 34.8, which are like I can here divide equation 2 by 1, T sine 34.8 divided by T cosine 34.8, that equals F over mg, and from that I can calculate that force to be mg tan theta, that is 90 times 9.8 times sine 34.850, and that is going to be 610 in newtons. Now the work done by the tension is 0. Okay, and I will say here the tension is acting, and it is acting at that direction, And we know also that the work total is 0 because the object now it is at rest, then there is no motion. The W for the worker is going to be equal minus the work done by gravity, and that is going to be UG final minus UG initial, and that is going to be mg times h, which is 90 times 9.8 times 0.626. Then the work done by the worker is going to be 552 joules. Now, the conservation of mechanical energy. Now we are going to include here just the gravitational potential and the kinetic. For the first stage, we are going doing this like gradually. We call this the total mechanical energy as kinetic plus UG, or kinetic energy plus potential energy. Now, some of the quantities we know that they're gonna have the same value at all the points. This is the total mechanical energy. When only the force of gravity does work on the system, the total mechanical energy of the system is gonna be conserved. And this is one of the ways of expressing conservation of mechanical energy. K1 plus UG1 should equal K2 plus UG2. What does that mean? That the total of the two energies is going to stay the same, but the shares might change. Then I might have at one instant all my energy is gravitational potential energy. At another stage, maybe it's going to be half-half. At another stage, I might have all kinetic and zero gravitation. I might like have any kind of sharing between the two. Here I have this athlete is jumping in the air, and initially we can consider the surface of the ground to be where I'm gonna have the UG equals 0, and then all it was kinetic jumping with that velocity. Then he or she's gonna move to a highest point where they're gonna have maybe the maximum gravitational potential energy, but they're gonna have maybe also a little bit of kinetic, and then they're gonna move down, and then also it's gonna stay. Then at any instant here, I will find that the kinetic plus the gravitational potential energy is gonna be equal to a constant. Now, when we have sometimes other forces other than gravity acting on the object, and this is when I have, for example, air resistance, or when I have like friction. These forces, we are going like to talk about them later. We call them non-conservative, or here we they suggested we can call that W other, and that is going to be less than 0. And then I will say we need to include this in the conservation of energy, because I will say we will have the E is gonna decrease here. And why it is decreasing? Because there are other forces that they are doing a work that we cannot reuse again, or they are converting energy into other forms that we are not able to reuse again. Now, let's work with this problem here. I have a small rock with mass 0.20 kilogram is released from rest at point A, and it is at the top edge of a large a spherical ball with radius 0.5. Then I can say that point A, it is at 0.5 meters. Assume that the size of the rock is small compared, like I will consider it as a point particle, so that the rock can be treated as a particle, and assume that the rock slides rather than rolls, because if it is rolling, it's going to be another story, which we will talk about it later. The work done by friction on the rock when it moves from point A to point B at the bottom of the ball has magnitude 0.22 joules. Then there is a rough surface here, and there is work done by friction. Between points A and B, how much work is done on the rock by the normal force and by gravity? Okay, now I need here, in order, okay, I'm gonna talk about one part at a time. Now, when I look at this problem here, you're gonna find for A, like I will, the object is gonna move along the, curve. The normal here is gonna be always perpendicular to the, okay, here, I will show. Okay, the normal here is gonna be always perpendicular at any point. At the point A. Okay, and is gonna be, sorry, it's not gonna be at any point. I said at A is gonna be 0, and then is gonna be the maximum at B, because when you look here, is gonna be this way. The stone is gonna be here, or the rock is gonna be here. Then the maximum is gonna be here. Now, mg is going to be constant, and always it is pointing downward. Fk is going to be variable because it will depends on the normal, right? Because it depends on the normal, then mu k times the normal, then since the normal is changing, then Fk is going to be variable. Okay, what was my, yeah. Okay, then at point A here, how much work is done by the normal force? Okay, then I will say here we're gonna find that the normal is gonna be 0, and here the work done is gonna be the maximum. What I can do is I can say that the work done total is going to be equal to the work by weight, the weight by, work done by weight, work done by friction, and work done by the normal. This is at point A. We are going to find that this is going to be 0, and the weight is vertical, and I will say this all equals to the change in the kinetic energy. I can use conservation of energy to find what is going to be the final velocity of the object at B. Okay, because I can say here it was released from rest, then it has mgr, which is the gravitational potential energy, minus the work done by friction should equal the kinetic, and from that I can find what is going to be the final velocity. I can also calculate what is really the work done by gravity, and that is going to be minus UGF minus UGI with a negative. And remember, when it's going to come here to this point, I can consider this is my 0, and therefore I will be able to calculate the work done by gravity to be 0.98. Now I can then here say the work done by mg is going to be the work done by friction plus the kinetic energy, and from that it is again 0.98. Like I can do this using the two methods. This is like answering B. What is the speed of the rock at its reach point B? Of the three forces acting on the rock as it slides down the ball, which are constant and which are not? Of course, we said like the force that is constant, it is the mg, and the normal is not constant, and therefore Fk also is not constant. Of course, just as the rock reaches the point B, what is the normal force? It is due to the bottom of the ball is going to be the mg as it is reaches B. All right, now here work and energy along a curved path, we can use the same expression. Actually, I should be doing that example after this one. Okay, yeah, but it's like again it is like it is an expression that we can use in both cases. Now here we are showing you the energy bar diagrams. For example, here at this point, this is where the object was released, and then it was here at point H. We can actually draw the two diagrams. Here we send that object with the maximum velocity, and I will say we're gonna have mostly kinetic. I can choose my level to be y0 equals ug equals 0, but my E is gonna be the total of the green plus the 0, and then it's gonna be this here yellow. Now when it will reach like a point like in here, we're gonna find that with these here different angles, we're gonna find that it's gonna have some kinetic and some gravitational at this point H, because it is at a y from my reference and still have kinetic. The elastic potential energy, it is related to the changing the shape of the spring, which means it was stretched or it was compressed, and the elastic potential energy is going to be 1/2 kx squared, where x is going to be the stretch or the compression in the spring. Here, this diagram showing how a spring does work on a block that is stretched or compressed. Here the spring, the first one, A, it is relaxing, then that x is 0. It is not stretched, is not compressed. At B, it is stretched by that distance h2, and then it does negative work on the block. The reason is that the motion is in one direction and the restoring force is in the other direction. As the spring relaxes, it does positive work on the block, because now the block is going to be moving in the same direction as the force. And then here a compressed spring also does positive work on the block as it relaxes. This is the graph of elastic potential energy for an ideal spring. It is a parabola like y equals x squared. Elastic potential energy always it is positive because that x it is squared. I'm gonna stop here. I'm gonna have it the rest in another video.